we had completed chapter number 25. So now we are moving to chapter number 26. Okay, you people, I hope you people are studying. I hope you are able to access the material, the recording which I am able to leave on the Google Drive. Are you able to get it? Anyone? It looks like nobody is even bothering to study. Anyone? No, I don't know. I really don't know what's happening. Why am I not able to connect with you people? Did any of you go through the material? Could you access the material first of all? Well, that means from today I'm not going to share any material. Give your attendance. I hope you know how to give your attendance. Please enter your full ID, okay, enrollment number. So again, once more, I'm asking this question. Could any of you access the material given? Nobody's studying anything. Yesterday, the lab submission also was miserable. It was very bad job. And hereafter, from next week for lab, there is going to be attendance, and you have to mark your attendance. People who come only will be corrected. Other records will not be corrected. Okay. So we'll set it in such a way that only people who come that particular class will be able to submit on LMS. This we are going to do from the next week. Now coming back to chapter number 26. Okay, we are with chapter number 26, and in this chapter we are going to see electric fields. Okay, so what is this electric field? Let us see. See, we all know what is a gravitational force. So gravitational force is a force that two masses can exert on each other. You know that the sun is exerting a force on earth, earth is in turn exerting a force on sun. Okay, so I am giving this example because these are perceptibly big examples. Okay, so there what happens is two masses, let's say the sun and the earth, are able to interact with each other. They are able to exert a force on each other, equal and opposite force on each other. Now it becomes difficult for us to really understand how two masses which are not touching each other, they are not touching each other, then how are they exerting a force on each other? It's a non-contact force. Gravitational force is a non-contact force. So how do you explain that? Okay, so this is where it became necessary to introduce the concept of fields. So the concept of field was introduced to explain action at a distance. To explain action at a distance. Similarly, I have a plus Q charge, I have a minus Q charge. You know that the force between them depends on the distance between them. It depends on the magnitude of the charges and on the square of the distance, inversely proportional to the square of the distance. But they are not touching each other. Then how do you explain this force? So once again, we have what is called an electric field. The concept of an electric field, which is going to explain how these two charges, and here I've deliberately written static charges. That means we are not talking of moving charges. We are still with electrostatics. How static charges, though they are not touching each other, they exert a force on each other. So that can be explained via what is called the electric field. Similarly, the gravitational pull between two masses not touching each other can be explained using the concept of gravitational field. So I've been using the word field. So now the question is, what is a field? You have to understand in general what is a field. So field is simply a mapping of a property in space and time. Mapping. You know what's the meaning of mapping, I suppose? Okay, if I have my XY coordinate system, every point in the space will have a coordinate X, Y, Z. So if I am able to map a quantity to every point like this as a function of X, Y, Z and time, then it's called a field. I'll give you an example for that. Let us have a furnace. I have a room. At the corner of this, I have a heater. Furnace means you won't understand. So let's have a heater. And let's say that the heater is switched on and there is a thermostat and the temperature of the heater is 1000 degree centigrade. Okay. Now, what will happen when you keep a heater like this? What will happen to the rest of the room? Anyone? What happens to the temperature in the rest of the room?
The room gets warm.
The room gets warm. And points which are closer to the heater, they are going to be warmer. The temperature there is going to be larger. And the points which are farthest will have a relatively lower temperature. Or in other words, it would be possible for me to map or write what is the temperature for every point XYZ inside that room. So this example that I have given here is the temperature field. It's called the temperature field written as a function of XYZ. Okay. Now this XYZ will happen after, let us say, 3-4 hours of this 1000 degrees reaching of this 1000 degrees. After 3-4 hours, if you see every point inside this room, you are not switching on the fan, then every point is going to have some fixed temperature. There is no time dependence. On the other hand, in the first 2 or 3 hours, what will happen is every point will have a temperature and that temperature will also change as a function of time. It will also change as a function of time. It will gradually increase as a function of time. Or I will have temperature as a function of x, y, z and time. So there are 4 variables. Now this first is called a steady state. It's called a steady state. Every point has achieved some temperature and it remains a constant with time. Or this is called a static field. It's called a steady state or it's called a static field. It's a static temperature field. But then when the temperature is rising as a function of time, then it is called a dynamic field. And remember, temperature is a scalar. So you can call it as a scalar field. So temperature mapping as a function of position or time is called a scalar field because temperature is a scalar. I'll give you another example. Instead of this, let us consider some tube. Let's consider a tube of uneven cross section. Okay, and let's say some fluids are passing through this. So there is an inlet, there is an outlet. Now, for every point inside this tube as the water flows, you will be able to draw a vector. For every point here, you can associate a vector, and this vector quantity will also depend on the position within this tube. Okay, or here, velocity is a vector, and the example that I've given here is a vector field. It's a vector field, and here you have velocity as a function of x, y, z if it's a steady flow, and velocity as a function of x, y, z, comma t if it is a turbulent flow. Okay. So I hope the concept of field is clear to you guys. It's just mapping of some property as a function of x, y, z and time. And time sometimes without time. Okay, and it can be a vector quantity, it can be a scalar quantity. Is this clear, guys? Yes or no?
Yes, ma'am.
Yes, ma'am.
One day I'm going to sit in the class, I won't teach anything, I'll just keep it on. I will just sit here for 1 hour and I want to see whether anyone even realizes I'm not teaching. Okay, so let's now go to the concept of, now we know what is a gravitational force, but then what is this gravitational field? Let us see. Okay, so let's say that I have the earth is there, it's a curved surface. Okay, I'm interested in points close to the surface of the earth and I want to know what is the gravitational field at various points. I want to know what is the gravitational field at various points. So what I have to do is I have to actually have a mass m0 at my point of interest and see what is the force experienced by m0. What is the gravitational force experienced by m0? You know that it will be its weight, m0 g. Okay, so like this, if I do for every point, then what I will get is gravitational field equal to F by m0. F by m naught. I have to just get the gravitational force on that mass and divide by mass. Or in other words, field is simply gravitational field. Gravitational field is simply gravitational force per unit mass. Per unit mass. So I have done this using a mass m naught. Instead of m naught, I can use some other mass also. Okay, but the definition for the gravitational field is G equal to F by m naught. Okay, now this m naught, what did I use this m naught for? I used this m naught to measure what is the gravitational field G. I used m naught to find out what is the gravitational field at different points in space around the surface of, above the surface of Earth. And since I used m naught to do this testing and finding out what is the gravitational field, this m naught has got a name. M naught is called the test mass. M naught is called test mass. It's a test mass. I'm putting a test mass at a point where I'm interested in finding the field and then studying what is the force acting on that mass. That force divided by mass gives the field at that point. Okay, and another thing that you should remember is if I'm talking about the field of the Earth, if I'm talking about the field around above the surface of the Earth, then the source of the field is going to be Earth. Earth is going to be the source of the field. So it is this Earth which is actually doing this job of exerting a force on m naught and pulling it down with a force F equal to m naught into G. So I take this force and then divide by m naught, I get what is the field at that point. So this Earth is called the source. Okay, and read this sentence. Gravitational field at a location is independent of the size of the test mass. Instead of using a 1 kg test mass, I can use a 2 kg test mass also. Because after all, it is weight divided by mass. So it doesn't matter what is the mass that we are having. Okay, but the G value that you're going to get depends on the source mass. So that is the reason why on the surface of the moon, above the surface of the moon, the gravitational pull is just 1/6 of what you have above the surface of Earth. So the gravitational field only depends on the source mass. It does not depend on the test mass. Okay? Now, did you understand this, guys?
Yes, ma'am.
Now the next question is there, can anything be a test mass? Can anything be a test mass is the question. Can the moon be a test mass? Or can Venus be test mass? Venus is also exerting a force on Earth, right? Moon and Earth are also exerting forces on each other. So can moon be a test mass is the question. Well, there is a restriction. What is that restriction? Let us see. There is a restriction on the size of the test mass. Okay, so there is a footnote on page number 588. You know what it says? The size of the test mass, okay, size of the test mass should be small so as to not disturb, the mass distribution, of the source, Will moon disturb the mass distribution of Earth? Think and answer this. Can moon disturb the mass distribution of Earth? What? Ask very simple. Yes. Give your reason for saying that.
Ma'am, moon exerts a force on the Earth due to which size occurs.
Very good, very good. You know that depending on the phase of the moon, you are going to have high tide and low tide. You know that tides, what is tide after all? Tide is simply a disturbance in the mass of the water bodies. Disturbance in the water body. So that means the moon is strong enough to disturb the mass distribution of the Earth. So definitely moon cannot be a test mass if I am interested in finding out the gravitational field above the surface of the Earth. So what is the restriction? The restriction is that the test mass should be so small that it does not disturb the distribution of mass of the Earth. Like for example, I can have a 1 kg object. The 1 kg object, if I take it to 10 meters height, it is not going to disturb the mass distribution. So it's okay. It can be a test mass. Okay. So this is how actually, using this concept of test mass, you are actually able to explain the interaction or the gravitational pull between two bodies which are not actually touching each other. Like for example, this is my Earth and this is my mass m naught. So there is a pull. Earth is pulling m naught is pulling Earth. Equal and opposite gravitational forces there. So how do you explain that? You can explain this using the concept of field of the Earth. The field is always represented by the letter E. F is represented by the letter F. I'm sorry, force is represented by the letter F. Field is represented by the letter E. Okay, so what happens is the Earth will have a field at every point, a field value at every point above it. It's got a field value at every point above it. So if you put at this point also, there is a value of the field. If you put a mass m naught there, now that force, then this m naught will experience a force equal to m naught into the field at that point. The field is G, you know it. Okay, so at that particular point, if I put a mass m naught, that mass will experience a force equal to m naught into E. Okay, so if there is a non-zero field, if there is a till there is a non-zero field at whatever height, there is a non-zero field. At that point, if you put a mass, that mass is going to experience a force equal to mass into the field at that point. If you go beyond that, where the field is, let us say, negligible or zero, then gravitational pull will become small. The force will be small. Okay, so using this concept of field, you are able to explain how two bodies which are not touching each other are able to exert a force on each other. Okay, and next thing is, why is this concept of field important? This concept of field is important because this is a very, very important line, because variation in field travels at the speed of light. Variation in field. If a field changes as a function of time, any change in the field, that information travels at the speed of light. It travels at the speed of light. What do I mean by this? If let us say that I have a mass and let us say that some heavenly body suddenly came and sat on this mass. Okay, then the gravitational pull between them has changed because the field at that point changed. So any information on field is instantly reaching your mass, that smaller mass. I have the big mass. Any change in this big mass is that information results in a change in the field at the point of at the location of the small mass, and at that point the field will instantaneously change. Therefore, the force also instantaneously changes. So that's the beauty of this concept called field. Okay. Now this concept of field will be translated directly into your electrostatics also. And here you will have a field called electric field. Electric field. There it was gravitational field. And what was the source of the gravitational field? The source of gravitational field was mass. Mass was the source of gravitational field. But here, for electric field, the source is charge. The source is charge. So here again, you will have two types of charges. One is called the source charge and the other will be called the test charge. Like there you had source mass and then you had test mass. Okay. What is the job of the source mass? The source mass job was to set up the field. And what was the job of the test mass? The test mass was used to measure this unknown field. Similarly here, you have a source charge. Let the source charge be Q. Okay, and I am saying that my source charge is a positive charge, let us say it is Q. All around it, there is a non-zero field. All around it, there is a non-zero field. Now, if you put a test charge Q naught at this point, if you put a test naught Q naught at this point, Q naught normally we like to keep just positive. I will explain the reason for that. If you put a test mass here, and let us say it's a positive mass, then what will happen is this mass, test charge Q naught, this charge will experience a repulsive force. It will experience a repulsive force given by F is equal to 1 by 4 pi epsilon naught Q naught divided by R square. if r is the distance between them. Okay, now I got my force. Now I want my field. So what should I do? Just now I told you, field equal to force divided by the test. There it was test mass. Similarly here it is test charge. Test charge. And just as I discussed in the case of gravity, here also there is a restriction on what can be a test charge. A test charge should be so small that it should not disturb the charge distribution of the source. It should not disturb the charge distribution of the source. Okay, so that is incorporated by writing E equal to limit Q naught tends to 0. That means your Q naught should be close to 0. Q naught tends to 0 doesn't mean Q naught is 0. What is the smallest charge we have on in nature? What is the smallest charge we have? Charge is quantized. What is that smallest charge? 1.6 into 10 to the power of minus 19. So max you can have an electron or you can have a proton. So if you want a positive test charge, then you will have a proton as a test charge or maybe some multiples of proton. Okay, so the smallest possible value will be this. So just as the same idea that you used in gravitation, you have to use here. So electric field is defined as limit Q naught tends to 0, F by Q naught. Now look at this. If Q naught is positive, what will happen? What will happen if Q naught is positive? If Q naught is positive, you can see that E and F will be parallel to each other. E and F will be parallel to each other. So just by knowing the force direction, I also get my field direction. So there are two things. Field is a vector. Field is a vector. It has got a magnitude, it has got a direction. Magnitude I directly get by dividing F divided by Q naught. But direction I'll be able to get if I take a positive test charge. If I take a positive test charge, then from this equation you can see that E and F will be parallel to each other. So the direction of the field also I will be able to get. But remember, your test charge can be negative also. If it is negative, your force direction will be opposite to the field direction. That's all. But mostly people prefer to keep it as positive. So here, look at this direction, this one. So you are interested, some source charge is there. You don't know what is that source charge. Okay, some source charge is there somewhere. And at this point P, you are interested in finding what is the field, what is the electric field. So what do? You put a positive test charge there. The charge is Q naught. And then see what is the force at that point. Force that this test charge experiences. Let it be F. Then you can say that this point P is going to have a field equal to F by Q naught. Is that clear? So field value of the point is measured by studying the interaction of the source charge with a test charge placed at that point of interest. And remember, field value is independent of the test charge. It depends only on the source charge. From here itself you can see. From this equation itself you can see F is equal to 1 by 4 pi epsilon naught Q naught by R square. Q is my source charge. Okay, what will be my field? My field is simply going to be, F by Q naught. Therefore, it is going to be 1 by 4 pi epsilon naught Q by R square. That is, it depends only on the source. It does not depend on the discharge. Okay, only restriction on the discharge is that it should not disturb the charge distribution of the source. Like for example, I have a metallic object. It is charged. If I bring a positive, I have a metallic object which is positively charged. If I bring a big charge body here, a large charge here, what will happen to these charges? These are mobile charges. These mobile charges will either, all of them will come this side or they will go back depending on whether it is a repulsive force or an attractive force. So by doing that, what have I done? I have disturbed the source charge distribution. Therefore, this fellow cannot be my test charge. So my test charge should be so small that it will not disturb the charge distribution of my source. Okay, so now here is an equation. We are talking of, I'm explaining how two charges Q1 and Q2 point charges are going to interact with each other via the field. So first case what we'll do is we will take Q1 as the source charge. We will take Q1 as the source charge. So my source charge is Q1. It is located at A. I'm interested in finding out what is the field at the point B. So what will I do? I will put a charge Q0 there. I will put a charge Q0 there and then measure what is the force on it. Force divided by Q0 will give me what is the field at that point. I call that field as E1. I call it as E1 because my source is Q1. Okay. Now, at this point B, I am going to put my charge Q2. At this point B, I am going to put my charge Q2. If I put my charge Q2, you know that Q2 is going to experience a force Q21 equal to Q2 into E1. Q2 into E1. Because E1 is the field at this location. You're seeing here. E1 is the field at this location. So at this point, if I put my charge Q2, Q2 is going to experience a force. And that force, by our convention, is F21 and it is equal to Q2 into E1. So I hope you understood how you can talk about the interaction of two charges Q1 and Q2 by talking about a field called E1. Now you will ask a question, why should Q1 be the source charge? Why not Q2? Yes, we can do that also. So look at the second set of pictures. Okay, so let us say that my Q2 is going to be the source charge, which is placed at the point B. At point A, I am going to later put Q1. Okay, so first what I will do is I will put a Q0 there, find the force, divide by Q0 and get the field. This field I call it as E2 because the parent source is Q2. Next what I do is I put my Q1 there and this Q1 is now going to experience a force F12. Q1 is going to experience a force F12. So F12 is going to be equal to, can anyone fill this? F12 will be equal to? Will be equal to? Q1 into E2. Q1 into E2. So in the first set of pictures, we have taken Q1 as a source charge and we talked about E1 as a field. In the second set of pictures, we have taken Q2 as the source charge and we have taken E2 as the field. Both the ways you can explain this interaction or the force between Q1 and Q2. Okay, and please remember, F12 will be equal to minus F21, but E1 is not equal to minus E2. Okay, so the field is not going to depend on the second charge, it's going to depend only on the source. Now let's quickly go to what is the electric field due to a point charge. So that is the simplest thing we can see. So let's have a point charge plus Q. And I want to know what the field is going to be. So what do? Put a test charge at the location of interest. Okay, so let's say I'm interested in finding what is the field at a point P1. So what do? Let this be at some distance R. So first I'll put a test charge Q0 there, find out what is the force, and then divide this force by Q0, then I get my field. So look at this, my field value will be 1 by 4 pi epsilon naught Q by R square into R cap. I have put a modulus for Q, which means whenever you are treating a source charge, never look at the sign of the charge while writing equation. Just take it as modulus Q. So the direction you should get from the force direction. Direction you should get from the force direction. Okay, like for example, in this case, you see here, if I put a positive charge Q0 here, it will experience a repulsive force. That will be the direction of the force. Therefore, force will be parallel to E vector. Therefore, my E vector also will be away from the positive charge. Away from the positive charge. Similarly, I take a point P2. I can do the same thing there. I can take a point P3. You can see here that P3 is far away from Q. P3 is far away from Q, and you can see that there is a 1 by R square dependence. There is a 1 by r square dependence. Or you can see that E is proportional to the source charge. It's also proportional to 1 by r square. And you also see that if the source charge is a positive charge, then the field lines are going away from the source. Field lines is a vector, so field lines are going away from the charge. You can see in all these three, E, they're all going away. Okay, so the equation for the electric field due to a point charge is going to be E equal to 1 by 4 pi epsilon naught modulus q by r square, and the direction is given by r cap. Okay, so that's the conclusion. Electric field due to positive point charge points radially out from the charge. Use this word, radially out. Why do we say radially out? We say radially out. If I say that this is a point, if I have a point, then three-dimensionally you can talk about points. All around it in 3 dimension, I can talk about points. I can talk about field at all these various points. Okay, so there is a radial, it is radiating out from that point. So radially out. Okay, that's the reason why it says points radially out from the charge. Okay, and if I have a negative charge, what will happen? If my point charge is a negative charge, what will be the field? All around it, the field will be Kiran Mai.
Yes, ma'am.
What will be the field if it's a negative charge, negative point charge?
It will be inward.
Inward. It's again going to be 1 by 4 pi epsilon naught q by r square. So that means I have a point charge at distances away from the charge, the field value keeps decreasing. It falls off as 1 by r square. That explains why force also falls off as 1 by r square. Okay? And another thing, if I have a positive charge like this, Q, now, if I construct a spherical shell around it, what can you say about the value of the field at a point P, at a point Q, at a point R? Anyone? Q is at the center of this spherical shell. I'm taking 3 points on the shell, P, Q, R. What can you say about the field at these points?
It will be equal at all points.
All of them will be equal because R is the same for all of them. So that means you can actually imagine spheres. You can imagine concentric spheres around the point charge, and at all points on this concentric sphere, the value of the field will be the same. There is what is called a spherical symmetry. What is called a spherical symmetry around a point charge. Let me write it here. Okay, next thing. So here, let us also look at it graphically. I have field versus distance from the charge. If I have a charge here, okay, charge Q, and I'm talking of distance away from the charge. At infinity, field is 0. At infinity, field is 0. Therefore, it will touch the x-axis at infinity. But as it comes closer, as you come to points which are closer, you find that the field value goes up. And at Q, the field will be infinity, or there is a 1 by r square dependence. I hope this reminds you of the force graph that we had drawn the other day. The force graph and field graph will look the same. Okay, now let us come to the principle of superposition. Let's come to the principle of superposition. Now, you are not always going to be working with a single class only. Class. So let's talk about the principle of superposition. So let's consider a collection of charges. You may not be always working with 1 point charge. You may have a collection of point charges. Then what happens? Let us say I have a collection of point charges. Okay, so here are my charges: Q1, Q2, Q3. All of them are at rest. It's electrostatics. and I am taking a random point in space. I am taking a point P in space. I want to know what is the field at that point. Now, the principle of superposition says that the field at that point will be the vector sum of the fields due to these three charges. Here I've taken three. You can take n number of charges also. This is the principle of superposition. So principle of superposition can be written as a statement like this. The electric field at a point due to a charge is independent of the presence or absence of the field due to other charges. See, Q1 doesn't sense whether Q2 and Q3 are there. It doesn't bother whether Q2 and Q3 are there. Its field is going to be, let us say it is a negative charge. Its field is going to be E1 at the point P. Similarly, Q2 will behave as if only it is there. Q1 and Q3 are not there. So its field is going to be, let us say it is again a negative charge. So its field is E2. Similarly, E3. Okay. And therefore, the electric field at the point P will therefore be a vector sum of all these three. If E1, E2 and E3 are the fields because of Q1, Q2, Q3, then the vector sum of these will be the net field at that point. And you can extrapolate it to n number of point charges also. Okay, so that's what it is. E equal to E1 plus E2 plus E3, go on. Have we seen something like this in the previous chapter? Did we see something like this in the previous chapter? Yeah, what was that? Anyone? Anyone? F equal to F1 equal to F12 plus F13 plus F14. Remember? That is principle of superposition for forces. But for fields, this is the one. Only thing is you have to just understand that, okay, if I have a collection of charge, each charge is only going to see that point P. The point P it is going to see and there is a field because of that charge. Similarly, each of these charges, the presence or absence of any charge is not going to affect the field at that point. Each fellow's contribution remains the same only. So the net field will be the vector sum of all the fields. So that's your principle of superposition. Next thing is, if this is the principle of superposition, then can I take principle of superposition for granted is the next question. Can I take principle of superposition for granted? Is principle of superposition always obeyed? Is principle of superposition always obeyed? Or is there a situation where the principle of superposition can fail? Is there some situation where the principle of superposition can fail? Let's just answer this question. The principle of superposition can fail whenever the field is very, very large. Principle of superposition can fail when the field is very, very large. Example, in a lightning. In a lightning. Okay. Normally you see here, field is proportional to the source charge. Field is proportional to the source charge. But then in the case of a lightning, what happens is, you know that air is normally not a conductor. Air is normally not a conductor, it's an insulator, you know. Okay, but then in the case of a lightning, what happens is, there's a cloud, the cloud is having enormous charge, so the field because of this charge will be very high that it can exert force on the electrons of the air molecules, air atoms and knock out these electrons. Are you understanding what I'm saying? You have an atom, you're talking about an air atom, okay? So there are negative charges and positive charges. So the electric field, you know what the electric field will do? Electric field will exert force on the electrons and protons. But the force because of this lightning cloud will be so high that the force is so large that it can actually ionize the air. When it ionizes the air, what happens is more charges are produced. Because free electrons, ions are produced, so more charges are there. These fellows will further give rise to large fields. So more ionization will happen. Are you understanding? So in this case, what happens is, each can affect the other and create more and more charge and more field. Therefore, the principle of superposition is not valid. But in the case of small fields, yes, it is valid. What I'm saying may not immediately make sense to many of you. Like, for example, if I have to explain, this is my air atom, let us say it's an atom, oxygen is there, let us say. So what will happen is if the field is very, very large, the electrons will start experiencing a pull, let us say. If it experiences the pull and the force is so large, what will happen is the electron gets knocked out, and what you are left will be a positive ion and a free electron. Think of this happening to all the air. So huge amount of charges will get produced, and these charges will further create more field, more charges. So that is called an avalanche effect. Do you know what's an avalanche? Have you heard of this word avalanche?
Yes, ma'am.
Yeah. Where do you hear the word avalanche? Where do you hear?
Sliding of snow.
Sliding of snow. Snow is not snow. Huge glaciers.
Like a land.
It happens in the Himalayas, for example. I hope you people know that even a clap can sometimes trigger an avalanche. A clap, a simple clap can sometimes trigger an avalanche. This clap is going to give rise to some shock wave. So it just starts a movement in one place. The movement of that ice further creates more movement of bigger and bigger masses, and the rest is just a big avalanche. So similarly here also, in the case of lightning also, what you have is actually an avalanche effect. So in the avalanche effect, there is no more electric field proportional to charge. Proportionality and all is gone. Okay, so in this case, principle of superposition will fail. I have asked another question also. Is principle of superposition applicable to magnetic fields? Yes, it is applicable. So that's the reason why you can have two magnets instead of one and create a larger magnetic field. Okay, is it applicable to time varying fields? Yes, it is applicable. I've just given you the answer. So here, let's quickly do a problem. Let's quickly do a problem. An electron is placed near a charged body and experiences a force of F equal to 3.6 into 10 to the power of minus 8 Newton along the plus y direction. Who is experiencing this force? An electron. An electron is going to experience this force. So let's say this is my plus y direction. Now, what is the electric field at this point? What is the electric field at this point? How do I do that? F equal to, E equal to
F by E.
F by Q. F by Q. So what is my force? My force is going to be 3.6 into 10 to the power of minus 8 along the plus y direction. So let me call it as J cap divided by, what do I write for Q?
1.6 into 10.
1.6 into 10 to the power of minus 19. But then the force direction will be opposite to the field direction. Why? Force and field direction will be opposite. Why? Because my discharge is negative. It's an electron. It's an electron. Therefore, it will be negative. So my field direction will be opposite to the force direction. Do you remember what I said? If I have a positive charge, then the force on the positive charge will be parallel to the field, I said. If on the other hand I have a negative charge, then the force on it and the field will be in opposite directions. So here, the charge that I have is going to be an electron. Electron is negative charge. So therefore, if the force is along the positive y direction, then the field has to be along the negative y direction. Okay, so somebody can just do it. If you do it, you will get an answer as 2.25 into 10 to the power of 11 along minus y direction. Okay, and tell me what will be the unit? What is the unit of force? What is the unit of force?
Newton.
Newton, yeah. And what is the unit of Coulomb? What is the unit of charge? Coulomb. So Newton per Coulomb is the unit of field. Okay, now let's go to the next part of the problem. What is the electric field? You found out. what would be the force exerted by the same body on an alpha particle placed at that location? So it's the same location. At that location, you already know what is the electric field. Okay. If instead of an electron, if I place an alpha particle, then what will be the force? What will be the force on the alpha particle? Force, field and charge, you know the relationship. Force will be equal to
Electric field into charge.
electric field into charge. In this case, the charge is going to be 2E, 2E plus 2E because it's alpha particle. And then the field you already know. You already know the field. So just put it. So 2 into 1.6 into 10 to the power of minus 19 into field you have is 2.25 into 10 to the power of 11. Okay, and the answer will be in newtons and the direction will be
Negative y.
negative y direction because it will be the direction of the field. Okay, so this problem basically tries to tell you that field only depends on the source, it does not depend on the test charge. So here you are putting two different charges at that location and showing that the force is different. Okay, now let's try this. In an ionized helium atom in which 2 electrons have been removed. So what is the charge? 2 electrons have been removed means what is the charge? It is positive. If 2 electrons have been removed, it is positive. And what is the charge? If I remove 2 electrons from an atom, then what is the charge of the ion? Please answer, don't type. Hey, if I chemistry, if I remove 2 electrons from an atom, I get an ion, a positive ion. What is the charge of the ion?
+2.
Plus 2, that's all. Plus 2E, that's my charge. Then, so I have removed, so this is my ion. Okay, in an ionized helium atom in which 2 electrons have been removed, the electron and the nucleus are separated by a distance of 26.5 picometer. Okay, so find the magnitude of the electric field of the nucleus at the location of the electron. So let's say this is my nucleus and let us say I'm talking about an electron here and the distance between these two will be how much? R equal to 26.5. What is pico? 10 to the power of?
-12.
Minus 12 meter. Okay, so at this point, I want to know what is going to be my field. Field will be radially out. That's the reason why I put this arrow. So can you find out? Field will be equal to 1 by, tell me the equation. 1 by
4 pi epsilon.
epsilon naught q divided by r square.
R
So
square.
let's, yeah. So 9 into 10 to the power of 9 into q is 2 into 1.6 into 10 to the power of minus 19 divided by r square. So what is my r? R is 26.5 into 10 to the power of minus 12 whole square. Okay, you will get a surprisingly large number. You know what is the field you will get? You will get 4.1 into 10 to the power of 12 Newton per coulomb. Isn't it a very big field? 4.1 into 10 to the power of 12 Newton per coulomb. That's a very big field. Can you explain why the field is so large? The field due to just this plus 2E, just the plus 2E, why is it having such a large field? Anyone? When nucleus is just having a charge plus 2E. Okay? Why is this field at that point so huge? Just look at those numbers and answer.
The point is very close to the nucleus.
Very good, very good. You said that. So the point is very, very close to the source charge. So it's very close to the source charge. The field is quite high. And as you move away from it, the field value falls off as 1 by r square. Okay, now let's try this. This will be the last problem for the day. So if you have three charges, Q1 equal to 1.5 microcoulomb, Q2 equal to 2.3 microcoulomb, X1 is the location of the first one, X1 equal to 0, let's call it origin, and X2 equal to L. Okay, that means the distance between Q1 and Q2 is L. Now, you are given a point P. Or locate a point P where the field is 0. Locate a point P where the field is 0. How do you do that? So let us take some random point P at a distance x from Q1. Next, what do you do? What will be, you have to apply the principle of superposition. So what will the principle of superposition say? It will say that the net field equal to the sum of the fields due to Q1 and Q2, right? And this has to be equal to 0. Next, what will be this? Q1 is a positive charge. So at the point P, the field E1 will be radially away from Q1. Therefore, my E1 is going to be this. Similarly, let's take my positive charge Q2. At the point P, the field E2 will also be radially away from Q2. Therefore, this is going to be my E2. Now, the sum of these two should be equal to 0. So, can you do it? So, for the first one, it will be 1 by 4 pi epsilon naught Q1 divided by x square. The second one is 1 by 4 pi epsilon naught Q2 divided by, what will this distance be? This distance will be L minus x. Okay, so L minus x whole square. Okay, and the sum of these two should be equal to 0. So if I take this as positive x, then this fellow is going to, E1 is going to be positive, E2 is going to be negative, and the sum of these two should be equal to 0. Okay, this negative I put because I am taking my E1 in this direction and E2 is going to be a vector along the minus x direction. That's the reason. Okay, now I can just leave out these two fellows. So I can say that Q1 by x square is equal to Q2 by L minus x whole square. Or I can say that x square divided by L minus x square is going to be equal to Q1 by Q2. Okay, or I will say x by L minus x is going to be equal to plus minus under root of Q1 by Q2. Okay, now just do this and then solve for x, taking L to be 13 centimeters or 0.13 meter. Taking L to be 0.13 meter, you solve for x. When you solve for x, this is simple, just do it yourself. When you solve for x, you're going to get two answers. I will get x1 equal to 5.8 centimeter will be one answer. Another answer you will get is x2 equal to minus 54.6 centimeter. I will get two answers because it's quadratic equation. I'll get a quadratic equation, so I will get two different values of x. Now, which of them, what is the meaning of these two numbers, you tell me? What is the meaning of 5.8 plus 5.8? What is the meaning of plus 5.8? From the origin, this was my origin, from the origin to the right, at this distance, x is equal to 5.8, I have my point P. Then, what is the meaning of minus 54.6? What is the meaning of x is equal to minus 54.6? Where is it? Where is that point?
It would be left to the way of Q
It will be on the left. It will be on the left somewhere here. Okay. Now, is it possible to have electric field 0 here? Answer. Use your logic and tell me. Can you have to the left of Q1 and Q2? Can you have field 0? Just logically answer. What will be the direction of E1 here? To the left or to right? E1.
Left.
Left. So E1 is going to be to the left. Okay. What about E2?
Left.
E2 also will be to the left. So can they both add and give 0?
No.
No, ma'am.
No. So that means, what do you conclude? What do you conclude? This is not a possible solution. This is not a possible solution. This is the correct solution. So sometimes mathematics would throw at us random answers like this just because it happened to be a quadratic equation. But then physics will not allow both those answers. So you have to look at which is the answer that physics is allowing and only write that answer. Okay. So with this, I am just winding up. So what I want you to do is, please, by tonight, I will be uploading this. Please, for heaven's sake, see whether you are able to get the material. If there is a problem, just let me know. And also